Chapter 10 Notes. Remembering from middle school, density is mass divided by volume. In physics, this is the symbol for density. It's a Greek letter rho. And usually when we use this formula, we use it as a substitution for mass. If you don't know the mass, density is something we can look up, and volume is usually something you can measure or will be given. Units are kilograms per cubic meter in physics. And we need to have the density of water memorized. From chemistry, it was 1 gram per cubic centimeter. In physics, it's 1,000 kilograms per cubic meter. Pressure is defined as force divided by area. It's measured in units of pascals. Force is newtons, area is meters squared, so a newton per meter squared is a pascal. Pressure in fluids. Pressure changes with depths. Our formula for pressure is rho GH, where H is how far below the surface you are. And you know, as you go below the surface in a swimming pool, the farther down you go, the more pressure there is. It's directly proportional to the height. Pressure at the top of an object is less than the pressure at the bottom of the object. We calculate both of these pressures because this height is bigger than this height. It's going to have a bigger pressure down at the bottom. I know force is pressure times area, so the force is also less at the top and more at the bottom. So this difference in the force is called the buoyant force. Buoyant force is the force at the top minus the force at the bottom. So if I plug these two formulas together and factor out the rho GA, H1 minus H2 is this height of the object. And we know that the area times the height is equal to the volume. So this is a formula for the buoyant force. And all these formulas we need to be careful about. There's two objects here. There's the cylinder in the water and there's the water itself. This is the density of the water and this is the volume of the cylinder. And I do want to point out this is the volume of the cylinder that's underwater. So if it's only partly underwater, it's just the part that's under the water that's used in the buoyant force formula. All right, sample problem. Will this log sink or float? They're giving us the volume and the mass. So it will float if the buoyant force is larger than the gravity force, and it will sink if the gravity force is larger than the buoyant force. So we're going to calculate both. Rho GV is the buoyant force, and mg is the gravitational force. And in this case, the gravitational force is larger, so the log will sink. The apparent weight is the difference between the gravity force and the buoyant force. If I subtract those two, the weight of the log is now 3920 newtons. That means if I go in the water and try to lift it up, I need a lot less force to pick it up than if it was on the land. Archimedes' principle says the buoyant or upward force is equal to the weight of the water that the object displaces. This is a video clip demonstrating that. We have a cylinder here and it weighs 29 newtons, and we're going to submerge it in water. And as it goes down, as we put it in the water, you see the water level rises. That is, the water is being displaced. It's moving upwards. And we know the volume of that cylinder is equal to the volume of that water moving upwards. All right, so now we're going to take that displayed water and run it off into a beaker. And what they didn't show here is that the volume that shows in this water in the beaker is the volume of the cylinder there. And then if we go ahead and weigh that water, it's going to weigh the exact same amount as the cylinder did originally. Let me back up real quick. Notice that the weight of the cylinder is less in the water. So the buoyant force is pushing upwards with 9 newtons here. So the cylinder only weighs 20 newtons when it's in the water. It weighs 29 when it's out of the water. So the buoyant force pushing up on it is equal to the weight of this water that was displaced. That is the Archimedes principle. So if we look at the formulas, the buoyant force, and this would be the force of gravity on the water. We'd use that formula for the Archimedes problem. For something that's floating, we're only looking at the portion of the block that is underneath the water when we're doing our calculating. So this buoyant force is equal to the weight of this water that's being displaced, not the top of the box, and it's also equal to the weight of the box itself. So we have three things equal to each other in the formula. I can substitute each of their values, rho GV, mg for the water, and mg for the box. They are all equal to each other. Again, we need to be careful of what the letters are. This is the volume of the block that's underwater, and it's also the volume of the water that will spill over the edge or the displaced water. The rho is the density of the water, not the block. For this one, the mass of the water that is displaced, it's the mass of this amount of water. If I look at these two formulas and put them together, I can substitute density times volume in place of the mass. And this gives us a little equation. G's are going to cancel out. It gives us a relationship for something that's floating. These two ratios will show the fraction that is underwater, the ratio of the densities or the ratio of the volumes. Another way they use Archimedes' principle is to calculate the specific gravity or the density of an object. What they do is hang the object and weigh it on a Newton spring scale in the air, and then they submerge it in water and they see how much the weight decreases. And from that change we can calculate what the density of the object needs to be. I've not seen a problem like this on the AP test, although it is something that they could give to us, so we should probably take note of the formula. Next type of problem is water pressure in a house. When you turn water on in your sink, the reason water flows out is because there's pressure in the line, and that pressure comes from a storage tank that is up high somewhere in the city. And we'll look at our rho GH formula. It tells us the pressure down at the bottom. We can calculate if we're 30 meters below that this is our pressure. Note that we assume the atmospheric pressure at the top and at the faucet are equal, so they cancel out. Otherwise we have to add them to our answer. This tank is open at the top, and we have gravity is pulling the water down, but there's also air on top of it, and air is also pushing down on it. That's the air pressure. This end at your sink, the air pressure is equal. Unless this height is really unusually large, they cancel out. So absolute pressure, when you're down at the bottom of the swimming pool, not only do you have the weight of this much water on top of you, but you have the weight of this much atmosphere on top of you. So the absolute pressure is the sum of both of those. The weight that we calculate for the water is called the gauge pressure, and this is the atmospheric pressure, P naught. So we call this the absolute pressure, is the sum of both of those. Pascal's principle is the next one. It says the pressure inside a fluid stays constant. And we use this inside of like your brakes in your car. Your foot will be pushing on one cylinder and compressing a fluid, and there's a cylinder near your brakes that pushes another piston out that will push on your brakes. All right, so pressure is force divided by area, so this is our relationship. This is also the principle behind a hydraulic jack. So this is a typical problem you might see. They have the area of the small cylinder and the area of the large cylinder, and you're trying to lift a 2,500 Newton truck. How much force do we have to push on it? So we're using our relationship F in over the area in equals F out over the area out. And it comes out to 125 newtons. So this ratio of their areas is, this one is 20 times larger than that one, and that means we can lift a force that's 20 times larger than the input force. End of notes.